Alright, this video is Unit 1, Lesson 6. We're going to be talking about modeling with radical functions. So we're going to first start with some equations that are in some ways really similar to the equations we worked with last time, but this time we'll see maybe a few more variables, and instead of having an answer that's like x equals 5, our solution is going to be an equation. So this first one, we have this little radical equation, and it says solve for E in terms of f and h. So when it says something like solve for E with a multivariable equation like this, it's asking us to get E by itself. So we're just going to try to get it so that the E is on one side of the equation, and then when it says in terms of f and h, that means that the thing that E is going to equal to is going to have the variable f and the variable h in it. So we're going to solve this equation really similarly to equations that we worked with yesterday, or last class period. So right now we have a radical is equal to f, so we want to undo it and get closer and closer to getting that E by itself, so we'll start by squaring both sides of the equation. Well, that leaves us with the equation E plus 7 all divided by h is equal to f squared. And now we have this denominator of h here that we would like to undo, so we multiply both sides of our equation by h. That reduces. And now we have E plus 7 is equal to f squared times h. It wouldn't be wrong to write the h first if you had it that way, or if you wrote it that way, it wouldn't be incorrect. The order of that multiplication doesn't matter. And then we have one final step to get that E solved for, and that is that we need to subtract 7. So that leaves us with the equation E equals f squared h minus 7. So we solved for E in terms of f and h. Let's look at an equation that is for the volume of a cylinder. The volume of a cylinder is given by the formula V equals pi r squared h. So we're going to work with and manipulate this equation. The first part says, if a cylinder has a height that's 4 times its radius, what is the volume of the cylinder in terms of r? So cylinder looks something like this. And so this is saying that the height, so the height of the cylinder, is equal to 4 times its radius. The height is equal to 4 times the radius. Well, we can use that. We want to know what the volume is in terms of r. So in other words, we don't want to have an h in that volume equation anymore. But we know that h is the same as 4r, so we can substitute that into our equation. Pi r squared. And now where we see h in the formula, we're going to substitute the value 4r. So we should simplify that a little bit, and it would be customary to write it as 4 pi and then r to the third power. We just combine these r's into one r with the power 3. So this would be the equation for the volume of this particular cylinder in terms of r, and that's a cylinder that's height is 4 times its radius. Okay, so part B says write an equation for the radius in terms of the volume. So we're going to solve this equation for r. We want to get that r by itself, solve for the radius. So we would take this equation that we started with, and the first thing that we'd probably want to do is, right now it has this 4 pi that's multiplying that r to the third power. We want to divide both sides of our equation by that. So now we have v over 4 pi is equal to r to the third power. And so we need to do a cube root to both sides of the equation. So we find that the radius is the cube root of v over 4 pi. So that's an equation for the length of the radius in terms of the volume. The last part says if the volume of the cylinder needs to be at least 30 cubic inches, what would be the smallest possible radius that would work? Okay, so if the volume is 30 cubic inches, this is giving me a value for V. We can put that into our equation for V. So that will allow us to solve for the smallest radius. The cube root of 30 divided by 4 pi. Now, if you're immediately typing this into your calculator to find the radius, you need to be a little careful here and group the 4 pi. Otherwise, your calculator might think you mean this, 30 divided by 4. And if you just put the pi, it's going to think that you want to multiply by pi. So you have to be careful to tell it that you want to divide by that entire quantity 4 pi. So be careful in your calculator to make sure that it's doing what you want it to do and not something different. So this one you don't want to do. You want to make sure that you group it like this one. And if you calculate that, you should find that the radius that we're looking for, the cube root of 30 divided by 4 pi, is equal to about 1.34. And that would be in inches because the volume was given in cubic inches. Okay, so that is dealing with volume. Here's a few other ones. The voltage equation, V is equal to the square root of P times R. And all of these in class the students worked on solving on their own. I'll show you a couple of them quickly. So on this one you would start by squaring both sides. So now you have V squared equals PR. And as we're trying to solve for R, we would then divide by P to get the equation R is equal to V squared over P. This next one, square both sides again, because that radical is already by itself, ready to be squared. H minus W divided by 5 is now equal to T squared. We'll multiply both sides of the equation by 5. So we have H minus W is equal to 5T squared, and our last step here would be to add the W. So we have H is equal to 5T squared plus W. And then the last one, Pythagorean theorem, we want to solve for B. This one has one part that sometimes confuses people. We would start by subtracting A squared. So now we have B squared equals C squared minus A squared. And then we want that B by itself. We're trying to solve for B, so we would take the square root of both sides of the equation to give us that B is equal to the square root of C squared minus A squared for the length of the sides of a triangle. Be careful here, this is not the same as C minus A. The root can't reduce those two powers separately when they're being subtracted from one another. You literally just have to leave it like this. So be careful on that. So in class we talked a little bit about why we use radical equations or when radical equations come up. Pendulum motion, if you've seen a pendulum, this is a picture of a pendulum, but it's sometimes a little hard to see what it is. They often have them at planetariums and things. They swing back and forth. and the length and time of the length of this one cycle of a pendulum and how long that cycle takes and the length of the pendulum itself are related by radicals. Flow rates are related by a radical equation. Specifically the nozzle pressure and the diameter of the pipe or the hose. And centripetal forces in physics and things, you'll use radicals quite a bit. Also, I think the growth rate of sharks is related by a radical equation. Anyway, they come up a lot, so that's one of the reasons we study them. Here's an example with the pendulum. So this equation here is the equation for pendulum motion. The T, capital T stands for the time of the cycle, so that would be one swing of the pendulum, and L is the length of the pendulum in feet. So the time is equal to 2 pi times the square root of the length divided by 32. First part of this is we're going to solve the equation for L in terms of T. So we want to solve for L. So we would probably start, we don't have the radical by itself right now, it's being multiplied by 2 pi, so we would start by dividing by 2 pi. So now we have the equation T over 2 pi is equal to the square root of L over 32. The radical is now isolated. So we can now do a power of 2 to both sides of the equation. And, you know, you could square each of those things individually, but I usually just leave it in that form. And now we have it equal to L divided by 32. And as we're working towards getting L by itself, we just have one last step, and that is to multiply by 32. So we have L is equal to 32 times T over 2 pi raised to the second power. Okay, this next question says if the swing of the pendulum takes about 3 seconds to complete a full cycle, what is the length of the pendulum? So it's giving us a time, that's a t value, and it's asking us what is the length, so it's asking us to find L. So we'll use this equation that we just solved right here for L. We know the length is going to be 32 times 3 seconds divided by 2 pi to the second power. Again, be careful with that 2 pi denominator. You want to make sure you group that if you're using a calculator to calculate this. So we can calculate this and find that the length of the pendulum would be about 7.3 feet. So if you had a pendulum that was 7.3 feet, you would, if you swung it back and forth, it would take 3 seconds to complete one cycle. Here's a graph of this. Whoa, where did my graph go? Sorry. And you can see we just found this has time on the y-axis and length on the x-axis. So 7.3 was the length we just found, and that corresponds with a time of 3 seconds. So if you look at a graph of pendulum motion, you can see that, you know, each of these problems we solve, it really just represents one point on that graph. If a pendulum was 12 feet long, how many seconds would it take to complete a full cycle? So this one is giving us the L value and asking us to find the time. So in this case, I would actually use the original equation before we manipulated it. The time is equal to 2 pi times the square root of the length divided by 32. And the length we're using in this instance is 12 feet. So we calculate that and find that it would take about the time is about 3.85 seconds. Okay, I'm gonna skip those two for the video. Alright, function d of h is equal to the square root of 2h can be used to estimate the distance to the horizon from a given height in feet. So this has to do with like how far you can see, you know, if there weren't obstructions or anything. Obviously, when you're in the middle of the land, there can be mountains and things that obstruct your vision so that you can't see all the way to the horizon. Or you couldn't see potentially as far as you could if it was flat. But anyway, so this function, the distance to the horizon is the square root of 2h. So I want to talk about boats because on the ocean, where it's nice and flat, you can see pretty far. So we're going to look at the Titanic for a second. The Titanic has a crow's nest, and the height of the crow's nest on the Titanic was 92 feet. So my question is, how far was the horizon, or how far to the horizon would it be from that height, so that if a sailor was in that crow's nest working as a lookout and had his binoculars or telescope using that to try to scout the horizon for problems, I want to know potentially how far he could see to the horizon. The crow's nest is right here on that forward mast. Okay. So, how far could a sailor potentially see? So, let's see. We want to know at a height of 92 feet. So, the distance to the horizon from a height of 92 feet is equal to the square root of 2 times 92. So the distance is, and this is function notation, if that looks weird, that 92, it's just saying the distance from a height of 92 feet. So if we calculate that, the square root of 2 times 92, we find that it is 13.6 miles to the horizon. In tests, at a speed of 20 knots, the Titanic had a stopping distance of about a half a mile. At the time that they hit the iceberg, they were traveling a little bit faster than that, at about 21.5 knots. If they had spotted the iceberg soon after it became visible, would they have had time to stop? I think for sure, yes. Probably within a mile they should have been able to stop, and yet their lookout didn't even sound an alarm until less than 1 minute before they hit the iceberg. So I guess the lesson is watch out if you're the lookout. They should have been able to stop. They shouldn't have had any problems, but somebody didn't do their job right, probably. All right, one more. A financial planner needs to figure out the inflation rate for his client's home. So to calculate the inflation rate, we can use this equation. So the equation is that the inflation is equal to the new price, that's P2, divided by the old price, P1, raised to the 1 over n power, and then you subtract 1. So I have a house right here, and we're going to figure out the inflation rate for this house. Here it is. This house is located in Cedar City, and all of the information we need is on this fabulous ad. So we're trying to figure out the inflation rate. We need to know P2, the new price. Well, it looks like the price they have set is $315,000. That is the new price of the home. We have some additional information right here. This price, 278,000, is the original price, and that was as of August 2010. Now the other thing that we need to know is our N value. N is the number of years between the two prices. So since this original price was in 2010, our N is going to be 7 years because it's now 2017. So let's put in those variables into our equation. So we need to put the new price divided by the old price. And we want to raise that to the 1/7 power and then subtract 1. Now your calculator can handle that 1/7 power just fine. It's a root, it's a 7th root, but you can put it in as a power like that and it'll be fine. So if you calculate that, you should find that you get an answer of I equals 0.018. Now inflation is typically reported as a percentage. I guess I should have said, and we talked about in class, that if you don't know what inflation is, the inflation rate is sort of showing you how prices increase or potentially decrease if inflation is negative over time, but inflation is a measure of how prices change. So the inflation here is 0.018, and if you're thinking about that as a percentage, if you remember that you can think about this as 1.8%, and oftentimes the little trick people use is to move that decimal 2 spots. So the inflation rate was 1.8% for this home. Let's work with this equation a teeny bit more. I want to solve this equation for P2 in terms of the other variables. So if we're trying to get P2 by itself, the first thing that we'd want to do is add 1. So we now have the equation I plus 1 is equal to P2 over P1 to the 1/nth power. So I want to make this power into the power 1. So we multiply it by n, or if you're thinking about reciprocals, it would be n over 1. But that's just the same as n. Any number divided by 1 is just n. So we're really just raising it to the n power. So we have I plus 1 to the n power is equal to P2 over P1. And then finally we would multiply both sides by P1, the original price. So we find that the new price is equal to the original price times I plus 1 to the nth power. So if we know an inflation rate and we know the number of years and the original price, we could calculate the new price of something. So let's do that with this other house here. The annual inflation rate is 1.95%. That's our I value, but we're going to put it into decimal form. And the original price of the home, P1, was $187,500. Wondering what the value, how much the value has increased due to inflation. We want to know the new value of the home. 8 years would be our N value in this case. So the new price is equal to the old price multiplied by 0.0195, that's our I value, plus 1, and we're going to raise that to the 8th power. And if you calculate that, you should find that the new value of the home is about 218,000, and we'll just round that to the nearest dollar, $826. So that would be the new price of the home. If you were wondering how much its value had increased, you would just maybe subtract that original value to find that it had gone up, the price had gone up by $31,326. So here's the new value. All right, so that's it. Next time in class on, let's see, that will be on Tuesday for A Day and on Wednesday for B Day, we will review. And then the tests will be given in class on Thursday and Friday next week. So if you're falling behind or if you're confused on any of these topics that we've talked about this unit, please come in and get some help. I can help you figure out the parts that you're confused with and get ready for your test that will be next week. Thank you.